Hey there, welcome to Physics Classroom, and today we are going to be taking a look at a very interesting topic we call waves. Waves. First and foremost, it is very important we know what a wave is. How do we define a wave? A wave is a disturbance which travels through a medium, transporting energy from one point of the medium to the other without causing any permanent displacement to the medium itself. Let's take an example, a very typical one, very common one. When you pick a stone, walk towards a pool, throw the stone into the pool, you'll find out that the stone will hit a point on the water and various circular ripples will be formed. It will be formed out from the point where the stone hits the water, where it dropped on the water, where it landed on the water. You see the ripple moving out that way. So the stone sets the disturbance on that water. Hope you understand. The disturbance itself is what we call water wave. So that's just the basic explanation for wave. Now let's look at the terminologies. Terminologies used in wave study. It's not possible for us to study wave without having to know various terms used in wave. The first term, number one, is what we call the period. Period is connoted by the symbol T. How do we define period? Period of a wave is the time taken for a wave to complete a cycle. The time taken for a wave to complete a cycle or a vibration is what we call the period. And period is measured in seconds. Take notes. The symbol for second is S. Number two, frequency. It's connoted by the symbol small letter f. How do we define frequency? Frequency can be defined as the number of cycles or vibration completed in 1 second is what we call frequency. Number of cycle or vibration. When we say cycle, we're talking about wave cycle. So numbers of wave cycle or vibration in 1 second, completed in 1 second. And the unit for frequency is in hertz or per seconds. Why? Because there's a particular relationship that tells us that period is equal to 1 over frequency. So if frequency is equal to per seconds, period is now 1 over per seconds. And that's going to give us seconds. So that's just it. Take note of that. Number three, the third term, amplitude. Amplitude. The symbol for amplitude is capital letter A. How do we define amplitude? Amplitude is defined as the maximum displacement reached by a wave. The maximum displacement reached by a wave. And the unit for amplitude is best put in meters. It could be in meter, it could be in centimeter, it could be in millimeter. It depends. So the fourth term is what we call wavelength. Wavelength. The symbol for wavelength is lambda. Remember our very first video on this platform was the Greek alphabet and its importance to physics. We talked about lambda coming from Greek alphabet. So lambda in this aspect, that is wave, symbolizes or connotes wavelength. Take note. Then how do we define wavelength? A wavelength is the distance between two crests or trough. The distance between two successive crests or trough. The distance between two successive crests or troughs. Distance between two successive crests or troughs. That's wavelength, and is also measured in meter as well. Now, when we talk about two successive crests or troughs, some of you might be like, what is crest, what is trough? I'm going to show you. Let me use a diagram to explain. so that it will be complete. Let's have it like this. So now, a crest. Crest. How do we define crest? I can say crest is the highest point on the wave. Please take note. The highest point. Highest point on the wave. That's crest. What about trough? The lowest point on the wave. Please take note of this. So now, look at this side. The highest points, these two are the highest points on the wave. Why these two, the ones below, are the lowest points on the wave? So distance between, look at, this is the point here. Highest point, highest point. This distance between these points and this point is lambda. Why distance between this, so we call this one the crest. This is also a crest. This lower part is the lowest point. It is what? The trough. Likewise, this also the trough. So distance between two successive crests is equal to lambda. The distance between two successive troughs as well is lambda. So please, let's take note of this. The fifth term is what we call wave speed. Wave speed. Wave speed. And what's the symbol for wave speed? That's V. V. How do we define wave speed? Wave speed is simply the distance covered by a wave in 1 second. The distance covered by a wave in 1 second. Please take note. The distance covered by a wave in 1 second. And it is measured in meter per second. Very, very important. Note this. There is a relationship that binds wave speed, frequency, and wavelength together. And that is V is equal to F lambda. It's very, very important. We're going to be using it to solve questions soon. And I told you previously that T is equal to 1 all over F. That is, F will be equal to 1 all over T. If that be the case, then we can say V is equal to lambda all over T. This could be 1 and this could be 2. Very soon, we'll be applying either of these two to solve some questions. So take note of this. The last term is what we call wave fronts. Wave front. How can we define wave front? Wave front is a common circle in which the particles of the wave are in phase. Wave front is a common circle in which the particles of the wave are seen to be in phase. There are two types of waves, which are the mechanical wave and the electromagnetic wave. The mechanical wave and the electromagnetic wave. Now, I will use a table to quickly differentiate between both. The first column will be for mechanical wave, while the second column will be for electromagnetic waves. For mechanical wave, look at, you realize that I started with M here and I started with E here. So the mechanical requires material medium. That's the first difference. It's okay. I've pluralized this so I can say they require material media for their propagation. Mechanical waves require material media for their propagation. What am I saying? Let me just give you some examples, typical examples of mechanical waves and their material media. I can say, for instance now, water wave that I used as an example to define wave the other time. Water wave is a wave, right? The material medium it requires is water. That's the medium it requires. Now, sound wave, right, is a mechanical wave as well. And it requires the medium air. String wave, like the wave from a guitar string, is a mechanical wave on its own, as it requires a material medium for its propagation. So the medium itself that this wave will require is what we call string. Take notes. You can see now that truly mechanical waves requires material media for their propagation. As you can see, some of the media are outlined here. On the other hand, electromagnetic do not require material medium for their propagation. Looking at the examples of electromagnetic wave, I use a particular code to further simplify everything. And it is GXUVIR, where each of all these letters are having their usual meaning. G here connotes gamma ray. The X connotes X-ray. Please take note of them. U connotes ultraviolet ray. V connotes visible light, or simply we can call it light wave. Under the light wave, this V, visible light, we have red, orange, yellow, green, blue, indigo, and violet, 7 of them. And they are already arranged according to their increasing wavelengths. So the I connotes infrared. Yeah, the I connotes infrared ray, while the last one, the R, connotes radio wave. Gamma ray, X-ray, ultraviolet ray, visible light or light wave, infrared ray, radio wave. Take note of this. Now, among these 6, gamma ray is known to have the shortest wavelength. Is known to have the shortest wavelength, and the wavelength increases down like this. Look at, following the direction of arrow, the wavelength increases. So the wavelength increases down the line. So we can say we have increasing wavelength here. Don't forget, there's a particular mathematical relationship that says V is equal to F lambda. If the V, that is wave speed, is constant, we now have our F to be inversely proportional to the wavelength. Hence, the higher the frequency, the lower the wavelength, and vice versa. If this is the case, as the wavelength is increasing along this line, so along this line, there is increasing wavelength. The wavelength increases, frequency decreases, penetrating power decreases, energy decreases as well. So take note of that. There can be questions that we ask, which of the following is having the highest wavelength? They can give you X-ray, visible light, infrared ray. In that case, your answer should be infrared ray, because that is going to be having the highest wavelength in that case. You would have come across questions like this in SSC, JAM, even university questions. So please take note, it's very important. The next difference is this. Mechanical wave cannot travel through a vacuum, cannot travel through an empty space, whereas electromagnetic wave can travel through a vacuum. Electromagnetic wave can travel through a vacuum, whereas mechanical wave cannot travel through a vacuum. And this takes us to the next aspect, which will be classes of wave. There will be classifying waves into two, the transverse wave and the longitudinal wave. See you in the next video.